Let's model population dynamics with a more accurate model. Let's go into nonlinear difference equations. In general, they are really complicated. Why? The idea is embedded in the lack of continuity. While for ODEs, we know that y needs to be a continuous function, so there is some control on how much it can go around. In difference equations, we don't have that. That means that yn can jump a lot, can jump in different directions every step, and so forth. So we have way less control about what is happening than what we usually do in ODEs. Still, we're going to try to do some interesting work. And we're going to be looking at this difference equation called the logistic difference equation. It is built on the continuous model for population dynamics that we worked on, but this is the discontinuous version. So we have yn plus 1 is equal to rho times yn times 1 minus yn divided by k, where rho and k are both positive. If we rescale, that means we introduce a new unknown, un, that we define to be yn divided by k, then we can simplify a little bit. And we now have the equation un plus 1 equals to rho un times 1 minus un, with rho a positive value. The first step that you want to do pretty much all the time when you look at ODEs or difference equation is finding the equilibrium solution. The equilibrium solutions happen when un plus 1 is equal to un, then we're going to call u. So we're going to solve u equals rho u 1 minus u. And it's a second order, it's quite easy. We have either u equal to 0 or u equals rho minus 1 divided by rho. So are these equilibrium solutions asymptotically stable or unstable? Let's first look at u equal to 0. We are thinking about what happens if we start in the neighborhood of u equal to 0. So if you start at a value of u0 that is small, does that initial condition go towards our equilibrium solution, or does it go away from our equilibrium solution? So this is our difference equation, un plus 1 equals rho un minus un squared. And we wonder, if un is small, what happens? Well, if un is small, then un squared is even smaller. So we are kind of claiming that the term that is squared, un squared, is so small that it doesn't matter. So we are approximating our second order difference equation. So nonlinear difference equation with a linear difference equation, claiming that the nonlinearity makes that term so small that we don't care anymore. So we're now approximating with un plus 1 equals rho un. That is something we have studied already, so we know the result. If the absolute value of rho is smaller than 1, then u equals 0 is stable. A theorem will follow stating when we can do this sort of approximations and when they actually give us a correct answer. But in this case, we can do this. So we have that u equal to 0 is always an equilibrium solution, but it is asymptotically stable only for absolute value of rho smaller than 1. So if we start with a rho that is too big, even if we're really close to u equal to 0, we're not going to be going towards u equal to 0. While if we start with a rho that is small enough and close to u equal to 0, then our population will tend to 0. What about the other equilibrium solution? The one we call the one at rho minus 1 divided by rho. We try to do something similar, but this is a not 0, so we'll assume that at un we have rho minus 1 divided by rho, that is the equilibrium we want to study, plus a small error. And we wonder if when we repeat the difference equation at the next step of the difference equation, is our small error getting smaller? Then we're tending towards the equilibrium, or is our small error getting bigger? So we're tending away from our equilibrium solution. So let's do it. Let's compute the next step, starting from the assumption that un is close to the equilibrium we want to study. Then un plus 1 is our difference equation applied to un. So our difference equation applied to the equilibrium plus a small error. And we do all the computations. And we want to find that un plus 1 is equal to the equilibrium plus a new error. What is the value of nu n plus 1 in order for all of this to work out? Then we have to study nu n plus 1, that is 2 minus rho multiplied by nu n, our previous small error, minus rho nu n squared. So now we're left with this new difference equation. The difference equation of the error that we're making. If this tends to 0, and then our error tends to 0, then our equilibrium is asymptotically stable. If this doesn't tend to 0, it doesn't matter what it tends to, then our error is not disappearing, so we're not getting any closer to our equilibrium solution. So let's look at this difference equation and try to understand if it tends to 0. Assuming that nu n is small. Well, we have studied this already, and yes, it does tend to 0 for the absolute value of 2 minus rho strictly smaller than 1. It's the same structure as we did before. So rho needs to be between 1 and 3 in order for our error to tend to 0. That means that rho minus 1 divided by rho is asymptotically stable, but only for rho between 1 and 3. So to look at it once again, for the equilibrium u equal to 0, it's stable for rho between 0 and 1, excluding 1. For u equals to rho minus 1 divided by rho, it's stable between 1 and for rho between 1 and 3. For rho equal to 1, that is not included in the stability of either, we only have one equilibrium, and it is stable. Rho equal to 1 is a special case, and it's where the stability changes between the two solutions. Also notice that rho equal to 1, the second equilibrium, the rho minus 1 divided by rho, is equal to 0. So we have two equilibria that tend to each other, touch each other, and go away from each other again. And where they touch, the stability flips between the two of them.